Hey everybody, welcome back. Today we're going to cover circuits. And electric circuits are possibly the most important topic that we cover in the entire year, simply because they're so ubiquitous. There are so many circuits all around us. Without circuits, we wouldn't have electric lights. We wouldn't have these computers that you're watching this on. We wouldn't have YouTube. Wouldn't have any of this stuff. So circuits are incredibly important and they're incredibly useful. And let's just start off with the very basics. For charge to flow in a circuit, what is necessary? Well, it's necessary to have a source of what we call EMF. And I've purposely drawn that E in that weird curly way because that E is actually the symbol of EMF. What does EMF stand for? Electromotive force. It's called electromotive force because of historical reasons. They didn't know what it was. They said, well, something's making this charge move. So they called it electromotive force, whatever makes those electric charges move. Turns out it's not a force at all. As we find out, the other word for EMF is just delta V. It's a voltage difference. They didn't know at the time what it was, but it's just a voltage difference. The units of EMF are volts. One reason that it's good to distinguish EMF from any voltage difference is simply because a capacitor, the delta V across it will change as the charge drains off it. Where for a battery or other EMF source, the voltage difference across that stays pretty much constant. So that's one useful way, that reason that we distinguish EMF from delta V. But anytime you see this E symbol right there for EMF, you could substitute delta V and no one would mark you wrong. So delta V or EMF is good for that. So you need a voltage difference and you need a complete conducting path from high voltage to low voltage, i.e. from the positive terminal of your battery or cell to the negative terminal of your battery cell or other power supply. We're going to learn about some schematic diagrams right now. Schematics are simply symbolic diagrams used to represent electrical circuits. And here are some selected ones. A wire, just a line like that. And a wire is assumed to be an ideal conductor with no resistance. A switch is just a wire with a little switch in it. We always draw those open. Why? If it were drawn closed, it would look just like a wire. A cell, a DC power source, looks like this. Now you may say, hey, that looks a lot like a capacitor. It does, but notice that one end is longer than the other. The positive and minus signs on there are not always written on there, but the long side of it's always the positive side of your cell. A battery is more than one cell put in series. Here's a 3-cell battery, although the term battery and cell are sometimes used interchangeably. An AC power source is drawn like this, with a little sine wave in there. We're not going to, AC stands for alternating current. We're not going to play too much with alternating current, but I thought you should know what that looks like. A resistor looks like this. A bulb, there's a lot of different ways to draw a bulb, but here's one of them. Little curly Q, which represents the filament, and a circle around it which represents the glass around the filament. A ground is like this. It's a series of ever-shortening lines. Sometimes there's 3, sometimes there's 4 or more, but a ground is anywhere you connect to. For example, on most appliances, it's the chassis of the appliance, the big metal box. For a car, the ground is the body or the frame of the car. Sometimes, like for our electric company, the ground is literally the ground, the earth. Crossing wires. Now, if you're trying to draw a circuit diagram and wires cross, that means that they're electrically connected. If you really want to emphasize that, sometimes there'll be a dot right there showing that they're connected. If you want wires to cross but not be connected, you've got to draw them like this. A little jump over like that. That indicates that they are not electrically connected. A capacitor we've seen before, it's just like this. An ammeter is like this. It's got a circle with an A in it because it measures amperes. A voltmeter is similar except it's got a V in it because it measures volts, voltage differences. An ohm meter looks like this. It's got a little omega in there. A fuse looks like this. And don't confuse that with an AC power source. So that pretty much covers some of the basic schematics that we'll be using.